Alright, let's continue with boosting. But before I continue with boosting, let's just recap quickly where we are. We're lesson 11, it was a very long lesson. We discussed decision trees. Decision trees is our final classifier in a series of classifiers that we discussed. From there we went to ensemble learning. Ensemble learning is very popular these days. What you do, you take a set of weak classifiers and you make a strong classifier. That's the basic concept. There's two main techniques. One is bagging. Bagging you do when you have a variance problem. And when we use bagging on trees, the algorithm is called random forests. Very powerful algorithm. Now when you have a bias problem, you will use boosting. I added variance here because whenever you do boosting, you want to manage variance as well in order to avoid overfitting. And the way it is done, for example, is that you limit the depth of your trees, anywhere from 4 to 32. Then we went on to discuss AdaBoost, which is a classifier. And how does AdaBoost work? Well, AdaBoost is adaptive boosting, developed by Freund and Shapiro in '96. And what you basically do is you take a set of weak learners or classifiers. These weak classifiers are stumps. What are stumps? Well, these are trees of depth 1. So this is my classifier H1, this is H2, this is H3. I'm going to multiply these classifiers with an alpha that represents the voting power. Alpha is inversely proportional to the error of a classifier. So if the classifier H1 has high error, it will get a low alpha. The stronger your classifiers go, the higher the alpha becomes. And basically, in the end, what you do, you just add these up. You have h of x, your final classifier is the sign of alpha 1 h1 plus alpha 2 h2 plus, and you go on until you stop. And when do you stop? Well, when you reach your target, or when all points are correctly classified. Now what about overfitting? Does AdaBoost overfit? Well, a lot of people will say no, and people will say yes from time to time as well. The reason why you could have overfitting is because if you have a lot of outliers, AdaBoost will try to classify them correctly and will go out of the way to do so. That's where you risk overfit. Okay, so let's now continue with the second technique, which is gradient boosting or gradient boosting machines. And there's, I would say, one important one called XGBoost, which is extreme gradient boosting. And that is very popular because it dominates the Kaggle competitions. These are globally led competitions, and you go and take a look at the winners of previous rounds, you'll see a lot of XGBoost. Now, gradient boosting can do regression or classification. Another one is Light GBM, developed by Microsoft. We will not go in detail in Light GBM. Definitely not. XGBoost, we will tell you what the difference is with traditional gradient boosting, and we will use it in the coding exercises of this chapter. XGBoost was developed by Tianxi Chen, and that was in 2014. So it's quite recent. Light GBM is even more recent. It's less than 3 years old. Okay, now before we start with boosting, there are two things. Yeah? One is I will explain the intuition of gradient boosting based on a regression example. From there, it's easy to go to classification because the only thing that differs is the cost function. Yeah? For regression, we will use something like the mean squared error, whereas for classification, we go for a log loss. Yeah? Minus, remember, for logistic regression, it was minus the log of the likelihood. So you see a log loss in classification. The basic idea behind gradient boosting is something that we call additive modeling. What is additive modeling? Well, you decompose a complex function, f of x, yeah, into a series of base functions or simpler functions. Remember, we in the dimensionality reduction section, which is optional, we discussed what singular value decomposition was. So you have a matrix A, and a matrix is a transformation in space. Yeah? Now A can be complex, yeah? But according to singular value decomposition rules, you can actually break down or decompose A in a rotation, a stretched, and another rotation. Yeah? So this is a rotation, this is also a rotation, and this is a stretch. Okay? So it's something similar, and you will find this frequently in mathematics. Another one we could think of are Taylor series, where you decompose a function in a series of polynomials. Yeah? So it's not so uncommon in mathematics. Now, let us continue here. And basically what we're going to try to do is we're going to decompose this signal here in three simpler signals. This one is y equals to 30. Yeah? When x is 0, y is 30. We're going to add the diagonal. Yeah, y equals to x. And then we're going to add the sign. Yeah, y equals sine of x. Okay? So if we add these three, we get this function. So we'll call this f1 of x, f2 of x, and this is f3 of x. Huh? f3 of x. And from this we will construct this complex or target function. And this is actually basically what gradient boosting is doing. It combines simple classifiers and make a strong classifier. So you can easily see that f of x here, f of x equals f1 of x plus f2 of x plus f3 of x. Yeah? Or, more in general, fm of x equals fm minus 1 of x plus fmx. Yeah? Because these two, that is f2 of x. Yeah, we add two functions. So, the target function when m is 3, yeah, it's f2 of x plus f1 of x plus f3 of x. Yeah? Now m is the number of functions. And it's the number of base functions you will have in order to produce this function. And this is something that we will need to give the system. So this is a hyperparameter. Now what's the link with machine learning and functions? Well, in machine learning we have we look for models. So these are simple models that we combine to a more complex model. And our models, we call them Y predict, and sometimes we call them H. It's the same thing. The H standing for hypothesis.